So as you can see, I'm from the Technical University of Denmark, from the Optophysics group, and I'm going to talk about distributed feedback lasers that we use for sensing. And I'd like to start with motivating my talk by looking at two figures that you might have seen in the presentation from Brian Cunningham today. And there you can see an image of some cells with a usual microscope here. And there's another image which I will call a label-free image here, which is showing us the refractive index on the surface. And you can see that cells are on the surface here, and from a wavelength shift of a passive photonic crystal, you can see that they are sitting on the surface. So this is a very nice technique, and it opens up for a lot of applications. So first of all, you can image cells, adhesion, and migration. You could also imagine if you can make an image of a refractive index on the surface, you can do multiplexed label-free biosensing. So you can imagine having a lot of sensing spots on a surface, and then for each of this spot, you can measure a wavelength shift of a photonic crystal transducer. And another thing that I think is really interesting is looking at microfluidics. There can be dissolution, diffusion, mixing. And in order to do that, what you need is, first of all, the low detection limit that photonic crystals can offer us, and also high frame rates. And with this technique here, you can get like an image in 10 seconds. And this is, of course, not enough if you want to look at things that deal with microfluidics where you have some mixing and diffusion. So to come to the outline of my talk, I will present nanoimprinted distributed feedback laser sensors that are basically refractive index sensors. And then I will show how we can use these sensors for label-free imaging, making videos of dissolution of sucrose in water. And I will show that this can be done with a frame rate of 12 Hertz and with no moving parts. So first of all, the nanoimprinted distributed feedback lasers, what is that? We have a substrate here. This is usually glass or plastic, and we have a waveguiding thin film, which is corrugated with a nanostructure with a period lambda here. And then this is a laser. You have a resonator from this grating. You have an active material in this waveguide. And then you have usually a pump at 532 nanometers, and you get some lasing emission out. If this is a so-called second-order distributed feedback laser, then you have laser emission out of plane. And you can calculate the wavelengths of this laser from this equation here, which basically is the Bragg equation. You look at the propagation constant of the mode in this thin film here, and then it has to fulfill this equation, and from that, you can calculate the wavelengths that you get from this laser. And my colleague Pietro will actually talk a bit more about this for passive photonic crystals later. Then these lasers, they look like this in our lab. We have glass wafers. We have ormocomb, which is a material that you can structure with ultraviolet nanoimprint. And it's doped with a dye, with a pyromethane dye that's emitting around 600 nanometers. And then we have a titanium dioxide thin layer on top, which makes this laser a very sensitive sensor. So it basically shifts wavelengths upon change in the substrate refractive index. And as you can see, we're doing that on 4-inch glass wafers. Then when you want to use this laser, you pump it with green pump light. So this is the glass wafer here. You can almost not see it, but you can see green pump light, a part of it going through, and you can also see orange emission in this case. And if you look at the wavelengths of that, you see you have a sharp peak, in this case around 560 nanometers, with a narrow line width. And then, as I said before, we use it as a sensor, so it changes wavelengths upon refractive index changes in the substrate. So everything that's on top changes the wavelengths, and then you can optimize these lasers here, and you can find the best thickness of this titanium dioxide laser layer, so this is 25 nanometer thickness here, gives you the strongest wavelength shift of your laser. And we have shown that you can get a detection limit in the range of 10 to the minus 5 refractive index units. So this is quite sensitive, but now I promised you to talk about imaging. So first of all, I want to look at imaging on a line. So we have a setup that you can see here. We have our pump laser. It's sitting in a dichroic mirror. It's reflected through a microscope objective and then onto our sample. And then this here is emitting this orange light. It's going through a dichroic mirror, and then via a tube lens and then a beam splitter. First of all, we make an image onto our CCD1 array here. And if we have a small pump spot, for example, we can see this spot here. And then we have a setup where we want to look at some simple fluidics in water. And this is again our glass wafer, and we have some PMMA on top with some wells. There are larger wells and smaller wells, and you can see later how we have been using them to study some fluidics. So we have seen that. So now how can we then image and measure for different positions? Then let's look at the imaging spectrometer down here. So what we do is we have an image on this CCD here, and we have another image which is hitting the entrance slit of our spectrograph, our imaging spectrometer. And then if you have an image like this, you can actually scan along a line what the spectrum of your laser is. And if you do that, and you're stable, you just have some water on top, you're changing nothing, then you basically get a line on your image here of the spectrometer. And so if you now have a setup like this, a larger fluidic well with the laser structure in the center, and a small well where we add a small piece of salt, then we can scan along this line how the wavelengths of our laser is changing. So let's look at this video here. You can see we add some salt up here, and then up here this is closest to the salt, and there the wavelengths is changing first, and down here it's happening later. So this is on one line, and when you look closer at these data, then you can see, for example, the dark red here corresponds to this position. There you have a wavelength shift which is corresponding to the concentration of salt in your water, and it's happening earlier here and later here. So this is very nice. It's actually a really good tool, I think, to study the dissolution of solid materials in different liquids. But then I also promised you to talk about imaging, so now we only have a line. What you can do to assemble an image is you can, of course, scan a lot of lines and assemble them to one image. Then what you would get is that you can maybe scan a line in 0.1 seconds, and then making an image by assembling a lot of lines will take you about 10 seconds maybe. But that means if it takes 10 seconds, you would only get 1, 2, 3 points here on this curve. And this isn't really enough to be able to resolve things that are happening on these kind of timescales. So what do? There, I'd like to present you the following structure here, which is a schematic of the laser again, but now it's not just having one grating period lambda, it's actually having, in this case, it's 3 different areas with different grating periods. And then you will expect that these areas, they lace, but they will lace at different wavelengths. And we actually built a laser like this, which you see in our optical setup again. And it has a lot of different areas here. They are all 25 micrometers wide, and they have different grating periods increasing from left to right in this picture. And it's a bit hard to see for the green, but you can see how the wavelength is increasing from left to right. So they're all different ones. And then we actually use this to identify our X position. So you can see here, this is again our image at this CCD. Now we see this rainbow colored laser. And then we're also having our imaging spectrometer image. And in this case, we use a cylindrical lens, and we use that to like focus the image in one direction so that all these different lines with different colors will be on top of each other. So we get all these laser lines into our imaging spectrometer, and then what we get from the CCD there is the Y direction up here, the same as here, and then the wavelengths, so we get the spectrum here. And then we can say, we can again identify our X positions from these lines. So if we follow all these lines, we can say how is the wavelength shifting, how is the refractive index on the surface changing for all these different positions. And this looks like this, is again this image here from our spectrometer. We have all these different positions, and what we do is we do a fit of all of these lines, trying to find the center wavelengths, which you can see from all these different colors here. And then we can scan on an area like this. And this is again a video. And now it's quite hard to see that the wavelength is actually shifting from left to right. You can maybe see it a bit when it jumps back after about 30 seconds. Oh, it's actually 45. But if you look at this in closer detail, for example, here this is the same image and we're looking at a cross-section here, then the spectrum you get is a lot of peaks, and we can identify the center wavelengths of these peaks with these colored spots. And then if you plot how these peaks change with time, then you can see that you have a redshift here, which means you have an increasing concentration of in this case, sugar molecules. And then, of course, this is not just done for one line, but we do it for the whole picture, and then we can actually make a video. So we add some sucrose here, and then after we add it, you can see that from left to right, the refractive index is increasing, and we can actually monitor how this concentration change is happening with a frame rate of 12 Hertz in this case, and no moving parts at all in the setup. And with this, I'd like to summarize. Again, I've been talking about nanoimprinted distributed feedback lasers, and I've shown you how we can do label-free imaging of dissolving sucrose and salt in water. Thank you very much for your attention.